Alright, problem number 1b, same idea as 1a. We have a series here and we want to find the infinite sum of this series. The problem is, this time we look at the series and this is totally not geometric. It's not of the form a sub 1 times r to the power of n minus 1. So we have a problem. How do we find the infinite series for something like this, some algebraic function that we don't know how to find the infinite sum of, because it's not geometric, it's not arithmetic. So what do we do? Well, that's why we have partial fraction decomposition. So let's focus on our the formula for our general term here, 1 over n squared plus 3n plus 2. And let's use our process of partial fraction decomposition to rewrite this fraction as the sum of two fractions. So remember, to do that, our first step is to factor the denominator. So n squared plus 3n plus 2 is going to factor as n plus 2 times n plus 1. And now we actually want to split this up into the product of two fractions. We don't know what the numerator of these fractions are yet. That's what we need to find. But we want each denominator to be one of those factors. So n plus 1 for one of them and n plus 2 for the other one. Okay, so now notice that what we have right here is an equivalence. We're saying that these two fractions are exactly the same. So we just need to figure out what values of a and b make that true. Now, to do that, we're going to have to do a little algebraic trickery. What we're going to do is we're going to multiply by our original denominator on both sides of this equal sign. So you can see on the left, we're going to get 1 times both those factors. So we're going to get n plus 2 times n plus 1 over n plus 2 times n plus 1 equals, on the right of the equal sign, we're going to have our fraction a over n plus 2. Well, we're going to need to multiply that whole thing by that original denominator, n plus 2 times n plus 1, and that's still over n plus 2. Then do the same thing to our second fraction, b times that denominator, n plus 2 times n plus 1, all over n plus 1. Now notice the reason we did that is because on the left, notice we've got the same thing in the numerator and the denominator for both of those factors. So that's just going to simplify to 1. On the right, notice in our first fraction we have n plus 2 in the numerator and n plus 2 in the denominator. So that equals 1. They're going to go away and we're going to be left with a times n plus 1 plus b times, notice similarly, our n plus 1s eliminate each other over on that fraction. So we're going to get b times n plus 2. And now at this point we could distribute that a and that b into those factors, and then we could rearrange our terms, combine like terms, and then we could actually solve this with a system of equations. But we know by this point that we have an easier way to do that. We've been calling it the cover-up method. And to use the cover-up method, we're going to ask ourselves, notice that we have, first off, a times something and b times something. Well, we want to make those somethings equal 0, because then that term is going to go away. So look at that first bit right there, a times n plus 1. What value of n will make that a term disappear? Well, if n is 1, then we're going to, if n is negative 1, then we're going to get negative 1 plus 1 equals 0. And so that whole term is going to cancel out. It's going to disappear. And so we're going to be left with 1 equals, well, negative 1 plus 1 is 0. A times 0 is 0. So we're just left with b times n plus 2. And when I say n plus 2, what I really mean is negative 1 plus 2, because you have to substitute that n value in wherever you see an n. So I should have put it right there too, but I forgot. So 1 equals b times negative 1 plus 2 is just 1, so 1 equals b. Okay, let's do the same thing, but now let's make it so our b term cancels out, goes to 0. Think about what n value you could substitute in there to make n plus 2 equal to 0. Well, yeah, it's going to be negative 2, because negative 2 plus 2 is 0. That will make my b term go away, and I'll be left with 1 equals a times n, which we said is negative 2, plus 1. And so just simplify inside your parentheses. Negative 2 plus 1 is negative 1, so we get 1 equals negative a, and so a equals negative 1. Now we can actually rewrite, go way back up to the beginning and rewrite this as a partial fraction. So let's actually substitute those values in that we see. Well, we know that a is negative 1, so we're going to get negative 1 over n plus 2, plus b is 1 over n plus 1. And now I'm just going to be nitpicky, and I'm going to rewrite that as 1 over n plus 1 minus 1 over n plus 2, rather than having that negative actually in my fraction like that. That's just how I prefer to look at it. Okay, but let's remember where we started. We did this whole partial fraction because we wanted to say, well, what is that value that we started with, that 1 over n squared plus 3n plus 2, what is that actually equivalent to in terms of a partial fraction decomposition? And that's what we got. We were saying that these two are mathematically equivalent. Go ahead, find yourself a common denominator. You'll see that they are actually the same exact thing. Put that fraction back together, you will get what we started with. But don't take my word for it. Do it yourself and show that it's true. But remember where we started. We started not really necessarily worrying about this weird expression here. We started because we wanted to find an infinite sum. So remember that we actually had this bit right here, 1 over n plus 1 minus 1 over n plus 2. We were finding the entire sum of that from n equals 0 up to n equals infinity, whatever that means, infinite sum. So, again, we're still kind of in a situation where it's like, well, I don't really know how to calculate that sum, because again, it's not geometric, it's not arithmetic, so we don't have a formula for it. But remember that this infinite sum is quite literally just the sum of each of the terms. I guess I should have started with a sub 0, so we'll pretend like that's over there, because we're starting with that n equals 0 there. But this literally means add up all of these terms forever. That's the sum we're looking for. So we don't have a formula for it, but let's just start listing some terms and see what happens. So let's list our first term, a sub 0. Substitute 0 into our expression there. Don't forget to substitute it into both and list the terms. 1 over n plus 1, if n is 0, we're going to get 1 over 0 plus 1 is just 1 over 1. So we're going to get 1 minus 1 over n plus 2. Well, n is 0, so we're going to get 1 over 2. So 1 minus 1/2 is actually our 0th term, a sub 0. And let's list now our next term, a sub 1. Well, substitute 1 into this expression here. We're going to get 1 over 1 plus 1 is 2, so we're going to get plus 1/2 minus 1 over n plus 2. Well, n is 1 this time, so we're going to get minus 1/3. And again, that bit right there, that difference represents a sub 1. And let's keep going a couple more times until we can really convince ourselves what's going to happen with this series. So let's go ahead and list a sub 2 now. A sub 2, we substitute 2 in for n, and we get 1 over 2 plus 1 is 3, minus 1 over n plus 2, so we get 2 plus 2 is 4. Now, I think we have enough terms here now we can recognize the pattern that's happening. Notice we have negative 1/2 and positive 1/2. And we have negative 1/3 and positive 1/3. And we have negative 1/4, and I bet if you find that next term, you're going to find that it's a positive 1/4. And then probably a negative 1/5 and a positive 1/5. And it's going to keep going like that forever. You're going to continue to get these pairs of terms that cancel each other out, that eliminate each other because they're opposites. That's going to happen forever. But notice in the front, that 1 never was eliminated by anything. So that is going to be the value for this infinite sum. It's just going to be that first half of the first term. 1. Woo!